Okay, this is just a summary of changing equilibrium position using Le Chatelier's. So Le Chatelier says there is a change to an equilibrium system, then the system will shift to partially oppose the change. Partly oppose, do the opposite. There will be more forward or back reaction, and then a new equilibrium will be established. So there's two ways of changing the equilibrium position: concentration and temperature. So I'm going to start. Concentration is two parts, the number of mole and the volume. So we'll look at the number of mole first. So if we use this example, the Haber process to make ammonia, then we've got one nitrogen and 3 hydrogen. Just write one in there. To make 2 ammonia particles. So if we add some reactants, then the system will try and remove the reactants and you'll get more forward reaction. If we remove reactants, then the system will try and replace those reactants, so you'll get more back reaction. If you add products, then the system will try and remove those products, so you'll get more back reaction. And if you remove products, then the system will try and replace those products, so you'll get more forward reaction. For all of these changes, K doesn't change. K only changes with temperature. So if I write down some numbers to prove to you that K doesn't change, if we just make K is products over reactants, the concentration of it. So if I just make up some numbers to show eventually these products over reactants will make a fraction, or there's two numbers involved. So if we did an example where we've added reactants, so if I add reactants and make this number go up to 5, then that is no longer at equilibrium. So that would be like our Q value, which is not at equilibrium. So you've made more reactants. If some of those reactants are used up to make products, this number could go down to 4 and that number could go up to 2. And therefore you see that now you have the same K value. So a half and 2/4 are the same number. So this is how the K doesn't change. Because you've added some reactants, now both of the numbers are larger because you've got more particles altogether, but they move until you get back to the same K value. Okay, so the other way we can change it is if we change the volume. So if we increase the volume, we decrease the concentration. So concentration is number of moles in the volume. If I have 1 mole in 2 liters, then my concentration is half a mole per liter. If I make this number larger, so make it 5 liters, 1 mole in 5 liters, then I've got 0.2 moles per liter. So you can just tell by looking that this number is a smaller fraction. 1 on 5 is a smaller fraction than 1 on 2. So the bigger you make that number, 1 on 100 would be a much smaller fraction than 1 on 2. The bigger you make the number on the bottom, the smaller the overall fraction. So the lower the concentration. Okay, so you increase volume, decrease concentration. Le Chatelier says it wants it'll shift to the side to partially oppose this, so it's going to try and increase the number of mole. It will never get back to what it was before. You'll never get back to the original concentration. It'll always be more dilute. So you have to shift to the side with more particles to increase the number of mole. So we've got 1 here and 3. We've got 4 particles on this side and we've got 2 particles on that side. So you will get more back reaction. Okay, so the opposite, if you decrease the volume, then you increase the concentration. increase the concentration, your Chatelier says it will partially oppose it to shift to the side with less particles. So you've got less number of mole. So that's the opposite. If you decrease the volume so this gets smaller, then you're going to shift to the side to make that smaller. So that would be more forward reaction. So the other way of shifting the position is if you change the temperature. So we've got exothermic reactions and endothermic reactions. So we're looking at this particular reaction as our example, this one. So if it's exothermic, then heat is being produced. You really should write in the heat and then just treat it as if it's a reactant or product. So heat, exothermic, you can tell it's exothermic because of negative enthalpy here. So heat is produced. So if we increase the temperature, the Chateliers would treat it just like as if you'd added product. So you'll get more back reaction to remove the heat. If you decrease the temperature, so you're removing heat, then you'll get more forward reaction to replace the heat. So you're busy cooling it down and it's busy making more heat. So more forward reaction. So endothermic is when the delta H is positive. So you're taking in heat. So write heat on this side and then just treat it exactly the same. So if you increase the temperature, you're adding heat, you'll get more forward reaction to remove the heat. If you decrease the temperature, you're removing heat, you'll get more back reaction to replace the heat. So in this case, these cases, the K value does change because you're making more of one number than the other, but you're not adding any more particles for those numbers to balance out. You're just taking something from one side and putting it onto the other side and the K will change. So for these ones, if we look at K here, K is products on reactants, concentration of the products over the reactants. So if we have more back reaction, we will get more reactants. So this number will become larger and that number will become smaller. So the fraction overall will decrease if the number on the bottom gets larger. And the opposite, if we decrease the temperature and you get more forward reaction, you get more products. So the number on the top gets larger compared to the number on the bottom. So a larger number means that you've got a higher fraction. So the K value goes up.